So today we're going to be looking at why so many drugs look like dopamine. So before we can begin drugs that mimic the structure of dopamine, we have to have an understanding of dopamine itself first. So dopamine is a neurotransmitter, and a neurotransmitter is simply a chemical messenger that sends chemical signals from one nerve cell to another cell. And this receiving cell could be either another nerve cell, a muscle cell, a gland cell. It really could be any other type of cell within your body. But these neurotransmitters are stored in the axon terminal of a neuron in small sacs called synaptic vesicles. And this right here is an example of a synaptic vesicle. As you can see, the little red objects are representative of neurotransmitters. And within these vesicles, there will be multiple of the same neurotransmitter. For these neurotransmitters to be released, an action potential or a signal has to travel down the axon of a neuron where it will eventually reach the presynaptic terminal. And when the message reaches this point of the nerve cell, it releases the neurotransmitters into the synaptic cleft. So as you can see here, the neurotransmitters within the synaptic vesicle move down and are kind of just like released here into this synaptic cleft. And the synaptic cleft is essentially a really small space that's filled with fluid that's in between the presynaptic neuron, or the neuron sending the message, and the postsynaptic neuron, or the neuron that is receiving the message. When the neurotransmitters are released into the synaptic cleft, they diffuse across the fluid and bind onto specific receptors on the postsynaptic neuron. These receptors only accept specific neurotransmitters. So for example, a serotonin molecule would not be able to bind onto a dopamine receptor that is pictured here, and a dopamine molecule will not be able to bind onto a serotonin receptor. This goes for all types of neurotransmitters. But once it binds onto the receptors on the postsynaptic neuron, this triggers an action in the receiving neuron that is either excitatory, meaning that the message is continued to be passed on, or it can be inhibitory, meaning that the message will stop at this neuron. Now, after these neurotransmitters bind and deliver their message, they have to be cleared from the synaptic cleft because their job has been done. Their message has been delivered. And these neurotransmitters are cleared via three processes. They either can diffuse away from the synaptic cleft, or they can be taken back into the presynaptic neuron via a process called reuptake, where they are taken back in through these protein transporter pumps back into the neuron and almost reused. They're recycled. Or these neurotransmitters can be degraded by an enzyme so that they cannot be used anymore. It can also be seen that medications can affect neurotransmitters. So medications can be designed to block the enzyme that breaks down a neurotransmitter so that more of it reaches nerve receptors, block the neurotransmitter from being received at its receptor site, or block the release of a neurotransmitter from a nerve cell altogether. Well, as we just learned, dopamine is a neurotransmitter. However, it plays a huge role in the brain. Dopamine affects pleasure, learning, concentration, sleep, motivation, and motor function. Dopamine plays an important role in addiction because drugs of abuse can increase dopamine release in the brain, leading to feelings of pleasure and a heightened sense of reward. If there is an imbalance of dopamine in an individual, this can be problematic. Diseases that are associated with low levels of dopamine include ADHD, Parkinson's disease, and restless leg syndrome. While on the flip side, diseases associated with high levels of dopamine include mania, obesity, addiction, and even schizophrenia. Many illicit drugs overstimulate your brain's reward center. So over time, with repeated drug exposure, a certain area of your brain becomes less sensitive, and you don't get the same feeling of pleasure from anything else but the drug. This feeling is due to a decrease in natural dopamine levels, since natural rewards such as eating no longer provide the same feeling of pleasure. Because of this, an individual often needs to take larger and larger amounts of a drug to produce the same effect. Dopamine serves as a reinforcement for remembering and repeating these deemed pleasurable experiences. So when drugs cause surges in dopamine, it's teaching your brain to remember the experience and go back to it. In the realm of illicit drugs, it can be found that methamphetamine has a similar chemical structure to dopamine. So here we have methamphetamine, and you can see it kind of has this ring structure here, as well as this piece that comes, this side chain that comes off. And this is cocaine. And this structure of methamphetamine allows it to enter the presynaptic neuron through dopamine transporters, almost as if it was being taken in through reuptake, or by diffusing through the neural membrane directly. So it can just come right in this way, or it can be taken up through this transporter protein. Once inside the presynaptic neuron, amphetamines force dopamine molecules out of their storage vesicles and expel them into the synaptic cleft by making the dopamine transporters work in reverse. So you'll have a methamphetamine molecule, it will come in through this transporter protein, and then it will come up to the synaptic vesicle and it almost kicks out a neurotransmitter. So it would come in here and it would take the place of a dopamine molecule, kick it out, and eventually all of these molecules would be kicked out and it would be replaced with methamphetamine molecules. And this will cause dopamine molecules to kind of build up here in the presynaptic neuron. And the presynaptic neuron doesn't want these, so this is expelled through the transport protein pump, but backwards. So typically a transport protein would bring a molecule in, but now they're going to be pushing the dopamine molecules out because these synaptic vesicles are not being released anymore. Another illicit drug is cocaine. Unlike meth, cocaine works by blocking the reuptake of dopamine by binding to the dopamine transporters on the presynaptic neuron. So cocaine comes in and it's going to block this transporter protein so that dopamine cannot be taken back up through reuptake. Even though cocaine and dopamine do not have the same structure, cocaine's tropane ring structure provides it with a similar enough shape to dopamine's benzene ring to be able to bind to the dopamine transporter protein and block the reuptake of dopamine. Normally, this would because normally this would be used for reuptake of dopamine, but now it can't. So this is going to cause a increase in dopamine in this synaptic cleft that can't be gotten rid of quickly enough. There's not enough degradation enzymes, and it can't diffuse away fast enough. So this results in prolonged and exaggerated activation of the dopamine receptors on the postsynaptic neuron. So these receptors are gonna just keep getting dopamine molecules that bind onto it. Drugs that can mimic dopamine structure are also used in healthcare. A class of drugs called dopamine agonists are often used to treat Parkinson's disease. And these drugs work by binding to and activating dopamine receptors, which leads to an increase in dopamine activity. Because Parkinson's disease is linked to a lack of dopamine in the brain, these dopamine agonists, such as apomorphine, pictured here, can create an enhancement of dopamine in the brain, which improves difficulties with movement and motor control. Adderall, which is used to treat ADHD, is an amphetamine that works in the same manner as methamphetamine because they both fall under the class of an amphetamine. They work the same way, where they're coming in through the protein pump and then forcing the expulsion of dopamine in reverse through the protein pump to create an abundance of it in the synaptic cleft. Now, unlike with illicit drugs, this increase in dopamine is good because individuals with these diseases have low levels of dopamine, meaning that they need this extra dopamine that is being released by the drug. Ultimately, many drugs can be seen to mimic the complete or partial structure of dopamine because of its importance and influence on so many of the body's functions. In terms of illicit drugs, this similar structure is used to take over and hijack the brain's reward system to create a dependency on the drug. Whereas in healthcare, these drugs can be used to treat dopamine imbalances by stimulating the neurotransmitter itself or its effects. Looking at this topic in retrospect to the General Chemistry 1 course, it can be seen that knowledge regarding molecular formulas and valence shell electron pair repulsion geometries is useful to understand the reasons why so many drugs share structural similarities to dopamine and can mimic its structure and effects.